So I wanted to take a minute today and go through number 6 from the projectile motion problem set. So I'm going to go through the steps, and I want you to pause at certain points to see if you can take it from there. The hardest part of these problems is getting them set up. Once they're set up, usually it's pretty straightforward. So I'm going to help you set it up, and then from there, I hope you will be able to get it, but if not, I'll walk all the way through to the end. So Sally wishes to throw a 2.8 kilogram pumpkin horizontally off the top of the roof in order to hit Mr. S's car. The car is parked a distance of 13.4 meters away from the base of the building below the point where Sally is standing. The building's roof is 10.4 meters high. Assuming no air resistance, with what horizontal speed must Sally toss the pumpkin in order to hit Mr. S's car? So the first thing I always say is draw a picture. So we have the building. Here's Sally. And then out here we have Mr. S's car. Sure, that's a car. There's the wheels. See? Perfect car. So what are our givens here? We know that the change in height here, our delta y, is equal to 10.4 meters. Now remember though, this is the pumpkin here. It's going to be going down, so it's a negative 10.4. We also know, we also know that the truck or car is 13.4 meters away. So 13.4 meters is equal to our delta x. So, and we talked in a previous note section, but the mass of the pumpkin will not change its falling speed. So we don't need to worry about that at all. It's just an extra variable thrown in. So let's go through our givens. So for our y direction, we have our delta y is equal to negative 10.4 meters. Our acceleration in the y direction is negative 10 meters per second squared. And we know our velocity initial in the y direction because she's throwing it at horizontal speed, and she's going to throw it horizontally off the top, which means horizontally is left to right, which means the VI in the y direction is 0 meters per second. Okay? And in our x direction, we know our delta x is 13.4 meters. We also know our velocity initial is going to equal our velocity final in the x direction. That's because our acceleration in the our acceleration in the x direction is equal to 0. All right? And what we are trying to find is our Vx initial So there are two major parts to this. First, we need to know how long it's going to take the pumpkin to fall, because no matter how fast Sally pushes it, it's still going to take the same amount of time to fall. That was from our notes on projectile motion. So it doesn't matter if she throws it at 100 meters per second or she throws at 1 meters per second, it's still going to hit the ground at the same time. And that amount of time is all she has to get it to hit the car. If it takes any longer than that to get to the car, then it'll hit too short, and if she pushes it too far, it'll hit past the car. So what we need to do then is to find the time from where Sally dropped it, or how long it takes for it to get from where Sally dropped it to the ground. So pause it here if you think you can work it through, and then you can double check with my work, but otherwise I'm going to keep working. So this is going to be our equation number 3, which is delta y is equal to velocity initial times t plus 1/2 acceleration times t, or time squared. All right, and so we know our delta y is negative 10.4 meters. Our velocity initial, and we're going only in the y direction, so our velocity initial in the y direction is 0 times t plus 1/2. And our acceleration in the y was negative 10 meters per second squared times time squared. So now if we simplify that, you get 10.4 meters is equal to negative 5 meters per second squared times time squared. So now if we divide negative 5 from both sides, that would give us 2.08 seconds squared is equal to time squared. And then we take the square root of both sides, and that's going to give us 1.44 seconds. And that's equal to our time. So that's how long she has to get it here, over to the car. Now that we have how long, and we have our distance in the x direction, and we know our v initial is equal to our v final, so our v average is the same as our v initial, because remember, v average is equal to v initial plus v final divided by 2. And if these two are equal, you'll just end up with this is equal to vi is equal to vf. So back to this formula. The other formula for average velocity is delta x, or change in position, over change in time. So that gives us our change in x is 13.4 meters divided by 1.44 seconds, which will give us 9.29 meters per second. So, and this is our velocity initial in the x, or our velocity final in the x, because it does not accelerate. And that's the answer we're looking for. So I hope this helped. If you have any questions, feel free to email me or send me a message on Remind. But otherwise, good luck on your test on Friday.